Hey guys. Hello, Professor.
Hey, how's it going?
It's going. Are we taking notes and using answers or just notes?
Just notes for today.
Okay, cool. Thank you.
Hmm. Yeah. So we're following up from the last lecture. So we're still on lecture notes 03 for truss equations. Mhm. Okay, it's 4 o'clock, so let's go ahead and get started today. All right, good afternoon, everyone. How's everyone doing today? How's everyone's long weekend?
Short.
Yeah, always too short. Yeah, I hear you.
Long weekend.
It was technically long, but yeah, these things are never long enough. But at least hopefully, one day off was, helped you guys out a little bit. Okay, so the plan for today is we're going to continue on with our lecture notes for the truss equation. So I think today will be the last day we cover trusses because we don't have too much. And then I think we'll do a little bit of the beam equation. Okay, so we're steadily kind of building up, so kind of the goal for this section is to kind of build up, a kind of what I think about as a library of different element types. And so far we've done springs, we're in the middle of trusses, and then, probably starting today we'll look at beams. And then after that, there's one more structural element that we'll look at is frames, okay? And basically using those, you'll be able to formulate these kind of direct stiffness, finite element problems, okay? Where you basically have slender structural elements that you can use to, to simulate any kind of structure, okay? Oh, okay. So last week I also graded your ANSYS activity 1, so you should see your grades for that on Canvas, right? And I also posted the solutions for that as well. And so if you want to see, my simulation results and you compare them to yours, and also kind of read what I've kind of written for the short answers, you can take a look at that as well. Okay, but overall, it seemed like everyone was able to do really well on the ANSYS activity. Everyone was able to get results. So that's looking good. Okay. And so remember, our next ANSYS activity will be in, I believe, 2 weeks. And so basically, we're going to finish up with, all this direct stiffness stuff, and then we'll come back to ANSYS after that. Okay. All right. Any questions on anything that I can answer before we get started?
How was your long weekend?
My long weekend, it was good. Actually spent so I during this pandemic I like to cook a lot, so that's kind of how I relax. So my fiance still had to go to work, so I kind of just stayed home and cooked. it's interesting because we my fiance has a coworker. He's like in his mid 80s, and like he lives in this retirement community. And apparently they like all these older people, they love to garden, and so they regularly produce like oranges and grapefruits and lemons all the time. And the thing is, like they grow way too many than they can consume. So my fiance is always coming home with like oranges and lemons and grapefruit. So I made grapefruit juice and orange juice, and I cut down our stash quite a bit, but it's never enough.
That's pretty cool though.
Yeah.
Nice.
Mm-hmm. Okay, so let's go ahead and get started. So I think where we left off last time was we did kind of a full 2D problem. So we kind of took it from start to finish. And so we found out, so we started from a 2D structure, and we saw, how to formulate the element stiffness matrices, combine them together into one global system, solve it, and then use that to interpret the results. Okay. So there's one more thing that you can do with these results. And this is actually kind of the more useful thing for finite elements, is to actually compute stresses. Okay, so that's the first thing we're going to go over to. And so remember, bars are the same thing as truss elements. So these are, we're still considering these types of slender elements right here. Visually, I like to just draw them as just slender rods, but they can be anything. Okay. And the thing with trusses is that they're exposed to either tension or compression. Okay. And so there's one in tension, and here's one in compression. Okay. And so, just for the sake of, our math here, and at least in terms of the element stiffness matrix, remember, both of these are the same because they're displacements and forces that are only driven down the axial length of the member. Okay. So when we get to beams, we'll consider, what happens when the forces are perpendicular to this. But for now, we're just going to consider this. Okay. And so, from our finite element solution, we're able to compute things like how much each of the ends of this bar displaces, right? And so in addition to the forces, we can compute how much these displace, right? So this might be U1 or D1, I should say. And this might be D2, okay? Where this end is node 1 and this end is node 2, okay? All right, so what we can do from this is we can actually compute the structural stresses that are felt inside this element, okay? And structural stresses are often something that you're interested in if you're designing any kind of structure or anything that's going to be loaded with forces or pressures, right? Because if you remember from like your strength of materials class, the stress is ultimately what determines whether, first of all, determines how much a member displaces, and ultimately it will tell you whether the structural member will fail and break apart. Okay, so a lot of times when you're performing finite elements, you want to solve for these stresses because that tells you whether your structure is going to break or not. Okay. Okay. And so the way that we can define stresses at least in a bar element is we can just simply take the force that's being applied at a node, okay, and then divide it by the cross-sectional area, okay. And just for the sake of putting this in terms of quantities that we knew before, I'll give this force a hat, and so that tells us the force has to be down the length of the member, or in other words, in the local coordinate system for that element, okay. Okay, and you can either compute the force at one end of the bar or the other end, okay. And so, on our bar element here, let's say that we have a force that's in this direction like that, and maybe a force that's in this direction like that, okay? And so when we compute the stress as F over A, that F is exactly the forces that that the bar experiences at its two nodal ends, okay? All right. And so let's just, for the sake of argument, let's just take the second one, okay? And so let's compute these forces, okay? Okay. All right, so we want to compute F2x. And so, we've actually already seen this. So if you remember from I think it was last time, we were able to compute what's called the reaction forces at all of the, at all the nodes on our truss. Okay. And so this is nothing more than the reaction force. Okay? And if you remember, the way that we compute it is we took our, we have to do this after we solve for the displacements. Okay. And so after we solve the displacements, what we have to do is just multiply our displacement solution by our original element stiffness matrix. Okay. Okay. And so mathematically, we did this, right? And so we said that F1 for hat, F2 hat is equal to K. Remember, K is AE over L times 1 minus 1 minus 1, 1. Okay. This is times D1 and D2, and both of these are hats. Okay. Right. And so remember, that's how we obtain our reaction forces, right? But in this particular case, we're only really interested in just, just one of these solutions, okay? Because we don't really need both, because, in order to compute the stress, we can just do it just from one of them, okay? And so let's just take the bottom row here, okay? And then we'll turn that into a matrix equation, okay?
Question.
Yep. Mm-hmm.
For the structural stress, I just want to make sure I have it right. Is it F1 hat dr2?
It's 1 or 2. So you can take either the left base of the left node or the right node. You can choose either one.
Okay, cool. Thank you.
Mm-hmm. Right. And so just to kind of save us some math, we're just going to take kind of the bottom equation there. Okay. All right. Any questions on this before we start to work that out? Okay. All right. And so if we write out the equation for the bottom one, we end up with this. All right. So I'm just going to take just the bottom row of that matrix. And so this is going to be minus 1 and 1. Okay. And this is going to be times D1 hat, D2 hat. Okay. Okay. And so, this is fine right here, but remember, generally we're going to be working in 2D. And so, in 2D, we want to transform these from the local system to the stationary system. Okay. And so in particular, we want to transform these guys. Okay. Okay. So let's go ahead and do that. And if you remember, the way that we do this is we multiply by a transformation matrix. Okay. I'm going to do one more thing too before we move on. Is I'm going to expand this to include the y coordinates as well. Okay. Remember, this kind of small 2x2 element stiffness matrix, that was when we were only considering displacement in one direction. Okay. Okay, so now our formula is F2x is equal to AE over L. And if we expand this guy, we get minus 1, 0, 1, 0. Okay. And then to that, we're going to multiply our transformation matrix. And then we're going to multiply our displacement vector in the stationary coordinates. Okay, so this is going to be d1x, d1y, d2x, d2y. Okay. Okay. So this is nice. So this form actually is nice because this guy on the right, this displacement solution in the stationary coordinates, this is what we've already solved for, right? So generally after we solve a 2D truss problem, we've already obtained the nodal displacements in the stationary coordinates, okay? And so by putting in this form, we can kind of already work with that, okay? And so now the question is just to kind of simplify what's left here into kind of a more simple form. Okay. So the first thing I'm going to do is I'm going to divide both sides by a, and so to get a on the bottom side here, okay? And so we're going to have f2x hat divided by a, okay? And this quantity is exactly what we're looking for. So this is our stresses, okay? And so this is going to be sigma. Oh, question. So are the y displacements like buckling? So not quite. So buckling is something that's actually quite complicated. So you can actually simulate that in ANSYS too. But what I mean by y displacements are just displacements that are transverse to the to our truss here. Okay. And so a y displacement, at least in the local coordinates, would be something like this. Right? So it would be displacement vertically like this. So it would be kind of perpendicular to the axis of the element. Yeah. Mm-hmm. Yeah, so right now we're we're not considering them. That's why we have zeros there. But when we remember when we transform things into the stationary coordinates, you might have a truss displacement going like this, and it has both an x component and a y component within kind of the stationary xy system. Oops, still purple. Okay. So by dividing by a, we get sigma on the left-hand side, which is good. And so on the right-hand side, what we have is E over L. Okay. And then we have the product of this kind of vector of -1, 0, 1, 0 times our transformation matrix. Okay. And then if you perform that multiplication, what you have is this. Okay. And so we have minus C minus S CS, okay, times our stationary displacement vector. Okay, and remember, C stands for cosine, S stands for sine, and so I just use the shorthand just because it's a lot easier to write. Okay, and so our formula here, so this is our formula here for the stress in that element.
You had a question in chat. He was asking no hats on the D vector.
Yeah, no hats on the D vector because that's we transformed that into the stationary system. Yeah. Yeah. So we took we started with displacements with hats because those were displacements in the local system that's local to that element. But we're not solving for those. Remember, when we solve 2D truss problems, we're solving for displacements in the global or in the stationary system. And so to kind of break this up, we removed the hats from the D's, and we also added this transformation matrix T right here, right? Because remember that transformation matrix is how we converted, we went from the local system to the stationary system. Yeah. Mm-hmm. And so basically, in order to compute the stress, this is something that you would do after you solve for the finite element solution, and you just have to plug it into this formula here. Okay, so you take basically the displacements that you solve for that element, and you multiply it by its Young's modulus divided by its length, and then you multiply that by this vector, which depends on the element's orientation. Okay, so I'll do a couple examples with this just so you can kind of see how that is. Okay? Because it's this formula right here, it's once you kind of know everything that's going on, you just have to plug it in. But kind of before you actually try it, it kind of seems pretty long, but it's not that bad actually. Okay. All right. Any other questions on this? Okay. All right. And so I do want to cover one more thing before we do our final example in this, and that's this idea of roller supports. Okay. And so roller supports are a special kind of boundary condition that you can have where basically, it will only knock out just one component of displacement, okay? Because up to this point, we've been using, what's called pin supports, right? So I think, up to this point, I've been calling them fixed supports, but, technically they're pins. And remember, with pin supports, we knock out both of the, the X component of displacement and the Y component, okay? And so basically before we've had something like this. And so we've had a support that looks like this, okay? And so when you do this, and let's say this is node 1 right here, right? And so when you see a support like this, you basically say that U1X or D1X, I keep using U, and D1Y, both of these in the global or in the stationary system, okay? Both of these are equal to 0, right? And if you remember from the example that we did at the end of last lecture, we for each of the supports, we knocked out 2 rows in the global stiffness system, right? And so we knocked out the row for the X displacement and the Y displacement. And so these are pin supports. Okay. Right. And so visually they look like something, that looks like it's something that can rotate, but they're kind of anchored into the ground. Okay. And so the other type of supports are rollers. And so visually they look like this. So visually they look very similar, except, the only difference is now, instead of being, anchored into the wall, they're on kind of like roller skates, okay? And so what this will do is this will prevent displacement only in the direction perpendicular to that surface, okay? Right. And so let's say that this is the X direction right here, okay, stationary X, and this is stationary Y, okay? And we'll say this is node 1, okay? In this form, since the roller is perpendicular to the Y direction, you can say that D1Y is equal to 0, while the structure is still free to move in the X direction, okay? That's because the roller is, it's only preventing motion into the wall, okay? And so these are roller supports. Right, so when you're doing these 2D truss problems, you have to really pay attention to what kinds of supports, are anchoring the structure. So if it's a pin support, you have to knock out 2 rows in our global stiffness matrix, okay? But if it's a roller support, you're only going to knock out 1 of the rows, okay? And sometimes this makes a big difference on the results because, sometimes there's some structures where, it'll be constrained in one direction, but not in the other one. And you kind of need to, solve for that other displacement, okay? Okay, and so, in the next example, I'm going to give you an example of this roller support and also how to compute stresses, okay? So this next example is going to kind of capture both of those situations. So any questions on this before we jump into that example? Okay. All right, and so this example here, we're going to have a 2-element system with only 3 nodes. Okay, so it's a little bit less intense than the last one, but I think it illustrates these concepts really well. Okay. And so we're going to have a structure that looks like this. And so at the top here, we're going to have a pin support. Okay. And our structure is going to go down like that. Okay. And on the bottom here, we're going to have a roller support. Okay. All right, so you can see here we have 3 nodes, and I'm going to label them like this. All right, so we're going to call node number 1 on the right-hand side. Okay. We'll call this node number 2 up top. And then we'll have node number 3 that's on the roller support. Okay. All right. So we'll give the elements letters. So the top element we'll call it element A. Bottom element we'll call it element B. Okay. We need to know the angles in between them. And so we'll say this is 30 degrees. Okay. And we also need to know their lengths. And we'll say the length of element A is going to be 10 feet. Meanwhile, element B, this will be only 5 feet. Okay. And so let's define the Young's modulus and the cross-sectional area for both of the beams. Okay. Right, so both beams are they're gonna be identical in terms of that. Okay. So both beams, or both trusses. My mind's kind of getting ahead of myself already. Okay. Let's say both elements have the Young's modulus. Will say it's 30 times 10 to the 6 psi. And then the area will be 1 square inch. Okay. All right. And so what we want to do in this problem is first we're going to solve for the finite element solution for all of the nodal displacements. Okay. Okay, so that's going to be step 1. And so, we're going to follow the same process that we did before. Okay. And then once we do that, we're going to compute the stresses in each of the elements.
Is that 30 times 10 to the 6th?
Yeah, 30 times 10 to the 6th. Mm-hmm.
Okay.
Oh, I forgot one thing. We need to load the structure. So we can't just fix it there. We need to actually load it. And so let's say that the end of the structure is carrying a load of 25,000 pounds. Okay. And that's going in the vertical direction. Okay. And so in other words, we're going to have F1y is going to be minus 25,000. Okay. Okay. And so we're going to start this problem exactly the same as we've done before. We're going to visit both of the elements, and so we're going to visit element A and element B, and then compute its element stiffness matrix.
Dr. Tran?
Yep.
When you're going about this process, should you always go from the lower number to the higher number? So for instance, you go like 1 to 2?
Yeah, that's a great question. So that's actually going to be my next point, because the how you compute the angles for these really depends on how the nodes are numbered. So that's a great leading question to what I'm going to do next. Right? Before I get to that, are there any questions any other questions on the problem setup?
Yeah, sorry, one more question. The A, what's the measurement for A? Is that?
Yeah, it's 1 square inch, so it's 1 inch squared.
Okay, thank you.
Yep. Okay. And so now let's go about computing the element stiffness matrices for both of these elements. Okay? So let's start with element A. Okay. And so since we're in a 2D situation here, the first thing you want to write down is what is the angle for this element. Okay. And so it's very tempting in here to just write 30 degrees because that's what's shown in the figure. Okay. But let me redraw the element A here for you. So right now we have this this situation right here where, you know, we can see that it's you know, rotated up and the rotation angle was 30 degrees. But what I'm going to tell you is that you know, when you write this angle here, you have to write the angle assuming that there's an arrow that goes from the lower numbered node to the higher one. Okay. And so what do I mean by that? And so basically, since we have node 1 on the bottom right here, we're going to draw an arrow going from node 1 up to node 2. Okay. And so we're going to have an arrow like that. And so this angle here that we actually write down is the angle that the arrow makes with respect to the positive x-axis. Okay. And so if we draw our positive x-axis like this, okay, and so positive x-axis is always going to go, you know, to the right. Okay. The angle that we want is actually this guy right here. Okay. Right. So in fact, the angle that we have here is not 30 degrees, but it's going to be 180 minus 30 degrees, which is 150 degrees. Okay. Okay. And so the angle that we want, and the angle that we want to plug into our element stiffness matrix, is the angle that the element makes with the positive x-axis. And that's if you draw a line, or if you draw your arrow from the lower numbered node to the higher numbered node. Okay. And so in this case, you know, node number 1 is our lower one. So we started there, and then we drew a line up to node number 2, which is a higher one. Okay. And then from there, we saw what angle that made with our positive x-axis, and we saw that angle was 150 degrees. Okay. Okay. And so with that, we're able to compute our cosine and sine. Okay. And so cosine of 150 is going to be, what is it? Minus root 3 over 2. Okay. And sine of 150 is going to be 1/2. Okay. And so we can plug that into our equation for the element stiffness matrix, and then we end up with the following. Okay. So we have element stiffness of A is equal to, okay. On the outside, we have the area of the element times the element modulus divided by the length, or AE or L. And then from that, we get 2.5 times 10 to the 5th. Okay. And then in here, you know, we have our 4x4 element stiffness, which is a combination of all the sine and cosine terms. Okay. And so let me go ahead and plug all those in for you. Okay. So we have 3/4 minus root 3 over 4, and then minus 3/4. And then root 3 over 4. Okay. Next row is minus root 3 over 4, 1/4, root 3 over 4, minus 1/4. Okay. Right. Minus 3/4. Root 3 over 4. Root 3 over 4, minus root 3 over 4, and then we have root 3 over 4, minus 1/4, minus root 3 over 4, and then 1 over 4. Okay. And then just so that, you know, because eventually we're going to have to assemble this into our global stiffness system, let's write out which nodes that these act on. So since this is acting on nodes 1 and 2, they're going to be the displacements x and y at nodes 1 and 2. So we have d1x, d1y, d2x, d2y. Okay. And so this right here is our element stiffness matrix for element A. Okay. Yes, so this is the element stiffness in the stationary coordinates. Because remember, this element stiffness matrix, or the formula that we went over last time, that was already transformed into the stationary system. And so this is so that, after we compute all the element stiffness matrices, we can combine them together into one global system. Yeah. Mm-hmm. So it's a little bit tedious when your angles are not either 90 degrees or 0 or 180 or something like that. So you really have to be careful with your arithmetic here, because there's a lot of places where you can have a typo. And remember, one thing that you can do to check is just to make sure that your element stiffness matrix is symmetrical. Okay, and so if you draw a line down the diagonal like this, okay, you should be able to reflect it and get the same kind of elements on the top portion and the bottom portion. Okay? So that's one thing that you can always check, just to make sure that you're getting the right entries. Okay. Any questions on this? Okay. And all of these examples I'm transcribing kind of exactly from the posted lecture notes. So especially this, believe it or not, this one's actually not that bad. So once we get to frames, it starts to get really crazy, like 6x6 element stiffness matrices that we have to do for 4 or 5 different elements. So and so when we're going through the lecture right here, I don't want you guys to focus too much on kind of copying down all the numbers, because all of that is in the lecture notes. And so I'm going to always do my best and try to write everything out, but don't feel like you have to kind of keep up, because all of that's in the lecture notes. Okay, I'd rather you guys kind of just focus and kind of think about kind of the process through which we're solving these problems, more than just kind of the tiny details. Okay. All right, so that's element A. And then we have element B. All right, and so just like for element A, we're gonna write out the angle for this. Okay, but we're gonna do the same thing. So we're going to write out the element here. Okay. And so if we take out element B from kind of from its environment, we have something that looks like this. Right? And so we have element 1 on the right-hand side and element 3 on the right. Okay? And so once again, if we draw an arrow going from node 1 up to node 3, okay, we can see that this arrow is going to the left. Okay, and so if we draw our positive x-axis here, okay, we can see that the angle that this forms is not 0 degrees, but it's actually 180 degrees. Okay, because we've kind of made kind of a full half rotation from the positive x-axis over to here. Okay, and so we're going to plug in 180 in for our element stiffness matrix. Okay, and so the nice thing about 180 is that a lot of the terms will go away, because cosine of 180 is just going to be -1. Okay. And then sine of 180 is going to be 0. Okay, so the fact that we have 0 here really helps us out a lot, because that's going to cancel out a ton of terms in our stiffness matrix. Okay. And so our element stiffness matrix looks like this. Okay. All right. So up front we still have AE over L, but since the length of element B is half that of element A, out in front we have 5 times 10 to the 5th. Okay. And then inside the matrix we have the following. Okay. So we have 1, 0, -1, 0, okay. 0, 0, 0, 0, okay. -1, 0, 1, 0, and then 0, 0, 0, 0. Okay. Right. And then just like before, we're going to write out the nodes that this acts on. And so this element acts on nodes 1 and 3. And so we're going to have d1x, d1y, d3x, d3y. Okay. And so here's our element stiffness matrix for element B. Okay. Right. So element stiffness matrices, it's at the end of the day, it's just kind of plug and chug. It's kind of plug and chug on steroids because you have to do it a lot. But it is kind of just plugging into that expression. So remember, just be careful. Make sure that you're kind of careful with your calculations, and this part you should do just fine. Okay. All right. Any questions on any of this so far? Okay. All right. And so now that we have our element stiffness matrices, we're ready to assemble them into our global system. And so since we have 3 nodes in this truss structure, we're going to have a 6x6 global stiffness matrix. So remember, for each node in our structure, we're going to compute both an x displacement and a y displacement. Okay, and so since we have 3 nodes, then we're going to have 6 different unknowns in total, and so that gives us a 6x6 system. Okay, all right, and so that 6x6 system is going to look like the following. Okay. All right, so I'm going to factor out a 10 to the 5th out in front, just because everything is going to be multiplied by that. And then we have the following system. Okay. So let me label all the columns, just to kind of make things a bit easier. And so I'm just going to focus on just the matrix portion here, but of course there's also the forcing vector that we need to account for as well. Okay. All right. And so let's go ahead and block out kind of the sections of this matrix where we need to insert our element stiffness matrices. Okay, so let's start with element A. And so element A, I'm going to use this kind of maroon color, or pink, I guess. Okay. And so remember, element A acts on nodes 1 and 2. And so let's box out the locations where that is. And so nodes 1 and 2 are going to be the first 4 rows and the first 4 columns. Okay. And so that's going to be element A right there. Okay. And then element B, I'm going to use this blue color. Okay. Remember, element B is acting on nodes 1 and 3. Okay. And so that's going to go like this. Okay. First, we have the 1, 1 block. And so we have our 2x2 system up here. Okay. Then we have the 1, 3 block. Then we have the other 1, 3 block, which is its reflection. Okay. And then we have the 3, 3 block down here. Okay. All right. And so let's go ahead and fill in the numbers here. Okay. And so I'm just going to kind of fill in kind of the end results, but just know that these are the results of insorting things in, and especially in this top left portion where we have this overlap on D1x D1y. This is the result of adding those guys together. Okay. And so we're going to have 6.875. And then minus 1.8, 1.08, minus 1.08, okay, 0.625, okay, and then we have minus 1.875, 1.08, minus 5 and 0. Okay. Then we have 1.08 minus 0.625, 0, 0. Okay. Then we have minus 1.875, 1.08, 1.875, minus 1.08, okay, and 0, 0, 1.08, minus 0.625, minus 1.08, 0.625, okay, 0, 0. All right, so that was the hard one. Okay, we have minus 5, 0, 0, 0, and then 5, 0, and then all zeros down here. Okay. All right, so that's that's what we get from just assembly. Okay, but we're not done yet because we have to apply our boundary conditions. Okay? So actually, let me write out the forcing vector down here. And so our forcing vector is going to be 6 elements long, okay? Because we have, X and Y forces that we're going to apply on the, on each of the nodes. Okay? And so let's start with our load, right? So let's start with our Neumann boundary condition. And so we only have one load in this problem, and that's acting on F1Y, okay? And so we know that on node 1, we're supporting a weight of minus 25,000. And so let's go ahead and plug that in. Okay. And since there are no other loads, we're just going to set everything else here equal to 0. So we have 0, 0, 0, 0, 0. Okay. Okay. And so those are all the loads, right? And now let's factor in the supports. Okay. All right. And so if we go back to our original diagram here, we can see that we have a pin support on node number 2. Okay. And so what this tells us is that d2x and d2y is equal to 0. Okay. And so that's going to knock out 2 rows in our global stiffness matrix. Okay. Meanwhile, node number 3 here has a roller support, okay? And so since the roller here is vertical, this means that d3x, only d3x is going to be equal to 0, okay? And so in total, we're going to knock out 3 rows in our stiffness matrix, okay? And so we're going to knock out the row for d2x, the row for d2y, and the node for d3x as well, okay? All right, so let's go back to our global system here. And so first, let's do the pin support on node number 2. Okay. And so node number 2 are these 2 rows here. And so I'm just going to take these rows and just eliminate them. Okay. Right. And so once again, if you know you're going to knock out these rows, you can just do that from the beginning. And so you don't have to go through the whole song and dance of assembly and then go back and erase all the hard work that you did. So, that's totally fine. This is kind of the way that I was kind of taught how to do this, is to assemble first and then do the boundary conditions. Okay. Right. And so remember, when we apply these supports, we've turned everything in that row to a 0 except for the diagonal component. Right. So the diagonal component, we're going to put a 1 there. Okay. And then that's it for d2y. Okay. And now let's apply the same thing for d3x and only d3x, because remember, we have a roller support there. And so applying that roller support to our global system looks like this. Okay. All right. And so now we've applied all the boundary conditions into our system here. Okay. Any questions on how we did that?
You just to clarify, you did that off of the diagram, right? Because
Yes.
of the supports.
Yeah. Right. Right. So when you're applying these support boundary conditions, you have to look back at your diagram and see which nodes are constrained by supports. And so in this problem, we had node number 2, which had a pin support. And so we're going to knock out both components, X and Y, for node number 2. Okay, so that's why we did the first 2 rows in orange there. And then for node number 3, since that one just had a roller support, we're going to knock out the row just for the X component. Okay, and so that's why we did the third orange row.
Okay, thank you.
Yep. Okay. And so at this point, normally you'd be able to plug this into MATLAB and solve this system, but we have kind of an anomaly in our matrix system here. Okay, and so I'm going to draw your attention to the last column, okay, and the last row of this matrix. Okay, and so basically everything that has to do with D3Y, right? All right, and so what you'll notice here is that everything that I've circled there are zeros. Okay. And so we have an entire row of zeros and an entire column of zeros. Okay. And so usually when this happens, they always happen in pairs. And so if you have an entire row of zeros, that means one of your columns is going to be all zeros too. Okay. And it's always the same one. And so in this case, since we have the last column is all zeros, that means our last row is also going to be all zeros. Okay. And so if you actually try to solve this in MATLAB, MATLAB's actually going to give you an error because it doesn't know what to do with a row of all zeros. And so when this happens, what you kind of have to do is you kind of have to look at your matrix and kind of eliminate this ahead of time. Okay. And so you have to kind of cross all those out. Oh yeah. So if you're trying the homework, and because this happens in the homework, I think at least once, then that's probably why MATLAB's kind of giving you an error. And so when you do this, you basically have to eliminate that from the system and just work with this matrix right here. Okay. And so this actually makes our system a little bit smaller. So actually let me cross out that guy too. And so instead of a 6x6, now we have this 5x5 system. Okay. And so what you can do now is you can plug this 5x5 system into MATLAB and then use that to solve for the displacements. Okay. And so if you do that, we can go ahead and plug these in and solve. And what we get is the following. And so you plug into MATLAB. And what you get is D1x is equal to D1x is equal to minus 0.0862 inches. Okay. D1y is equal to minus 0.55 inches, or 0.549. Okay. And then everything else here is going to be 0 because those are supports, right? And so we have D2x, D2y is equal to D3x, and also D3y. So if we're eliminating this this column and row, that means that D3y is going to be 0. Right? And so you're going to get 4 of these displacements equal to 0, and only 2 of them are actually equal to not 0. Right. So when you're plugging this into MATLAB, you're just going to ignore the last row and last column. So don't even actually plug it in. So when you're plugging into MATLAB, just make a 5x5 system that has everything without that last column and last row. Yeah.
If the zeros occur outside of the last row, do we still do the same thing?
Yep. Yep.
Okay.
So even if they sometimes you'll see a case where they occur in the middle, you're going to eliminate that. You're basically just going to cross it out and cross out the row, cross out the column, and then if it helps, you can rewrite the matrix as if that row and that column didn't exist. Yeah. Mm-hmm. All right. Any questions on this? Yeah, so the question is, how would the displacements look on the diagram? Yeah, that's a great question. So actually, let's draw the diagram again, and let's see how they look. Okay, and so we have element A here, and then we have element B. Okay, and so this is 1, 2, 3. And so according to our solution here, we have u1x is equal to minus 0.0862. Okay? And so visually, this looks like this. So node 1 is going to displace this way, okay, with a magnitude of minus 0.0862 inches. Okay? And so it's going to move slightly to the left. And then it's also going to drop down. Okay, so we have u1y, and so u1y looks like this. So u1y is minus 0.0 or 549 inches. Okay. Right. Meanwhile, node 2 and node 3 are just going to be fixed because they're supported by their supports. Okay. But in this particular case, we'd have node 1 shifting slightly to the left, but mostly down. And that makes sense because most of the load is going vertically. And so, we're going to have most displacement in the vertical direction. But because of the geometry in the structure, node 1 is also going to shift to the left a little bit, because we have this kind of angled bar that's supporting it as well. Okay. Okay. Any other questions on this before we compute the stresses?
Okay, so just to be sure, that whole thing where we have to eliminate a row and the column, that's only if like both the row and the column are all zeros or something. Like if I have a row of all zeros, but the column that a corresponding column isn't zeros, do I still get rid of it or what?
Yeah, it's a good question. So in these types of problems, they're actually always going to occur in pairs. And so you should never get a case where you have just a column that's all zeros, but then the corresponding row is not zero. And so, they should always kind of appear together. And so if you are getting a case where you have just a row is zeros, but not the column, then I would go back and kind of check to make sure that you put things in kind of the right places for the when you did the assembly and the boundary conditions. Okay, so the question is, why would a roller be used? Yeah, it's a good question. So it's just kind of a different way to constrain a structure. So there might be some cases, and we'll do this. I think we'll see this in ANSYS actually not until activity 4, where there will be cases where we just want to constrain in just one direction. Okay, so in ANSYS activity 4, so I'll kind of give you a preview of that situation. In ANSYS activity 4, we're going to simulate a car crash basically. Okay, so we're going to have a car, and we're basically going to ram it into a brick wall. Right? And so in that case, we want to constrain our, we don't want the car, which is kind of resting on the road, after the car collides with the wall, we don't want the car to kind of crumple into the ground. So we want to make sure that we kind of simulate the fact that the ground is there. So the car kind of hits the wall, kind of bounces off that, and kind of goes up. Okay. And so that's a case where you would want to constrain only in one direction, because we don't want to fix the car, because if we completely fix the car, then it wouldn't hit the wall. We only just want to prevent the car from kind of clipping into the ground, basically. So that's kind of one situation where you would want a roller. So it's kind of, you can almost think of it as just kind of part of your toolbox for helping you kind of simulate some realistic situations. Right. Yes. So John breaks up a great point in the chat too. So if you're making a bridge, then you would also want a roller support, so the bridge can expand and contract in one direction. That's a great point too. I think that's our ANSYS activity 5 actually too. So in ANSYS activity 5, we're going to be doing a bridge, and we're going to be applying a roller on that bridge as well. Okay. And so now let's compute the stresses in each of these elements. Okay. And so, you know, we have to kind of remember like an hour ago what we were doing. Okay. If you remember from before, you know, this is the formula that we plug in for the stresses. Okay. Because at this point, you know, we've solved for all the displacements at all the nodes. And so now we can just kind of plug those into this formula. And so sigma A is going to be E over L, okay, times a minus cosine, minus sine, cosine, sine, okay, times the displacement vector that this node is acting on. Okay? And so in this case, node element A is acting on nodes 1 and 2. And so this is going to be d1x, d1y, d2x, d3y. Okay. And so all you have to do is just kind of plug in your displacement solution here, and then plug in the angles for that guy, right? And so we know d1x is going to be minus 0.0862 inches. Okay. d1y is going to be minus 0.549 inches. Okay. Meanwhile, d3x and d3y is going to be 0. Okay. And we know that from before that the angle for element A is going to be 150 degrees. Okay. And so all I have to do is just kind of plug in, you know, 150 degrees into the cosines and sines. Okay. And then from here, you know, you just basically have a vector-vector product. Okay. So in the end, you're just going to get a single number. And so that single number for this guy is going to be 49,962 psi. Okay. Okay. And so since we got a positive number for this stress right here, we can say that this element here is in tension. Okay. And so it's being stretched more than it is being compressed. Right? Right, so that's element A. And now let's do the same thing for element B. Okay. Right.
Quick question.
So, oh yeah, what's up?
How did you get the PSI again?
Wait, say again?
How did you get to PSI, the 49,000?
So I basically, so what you have right here is a 4x1, or 1x4 vector, sorry.
Mm-hmm.
And here you have a 4x1 vector. And so all I did was I basically just performed the vector-vector multiplication. And so that means I'm going to take the first term and multiply it by this guy.
Mm-hmm.
And then the second term multiplied by this guy, third term, and fourth term. And then I just added all of those guys up together. Mm-hmm.
Thank you.
Mm-hmm. Yeah, the C's and S's are sines or the C's are cosines and the S's are sines.
I have a quick question.
Sure, what's up?
You wrote D3Y. Is it supposed to all be 2s?
Yes, that's right. Yeah, thank you. Yeah, thanks for catching that. Right. And so for element B here, you know, since this is bordering nodes 1 and 3, then we have to reflect that into this vector here. So it's, instead of, you know, d1x, d1y, d2x, d2y, our second set here is going to be d3x, d3y. And this problem, it doesn't really matter because they're all zeros, but, you know, for other problems, make sure you match up the right nodal displacements with the right element. Okay. All right, and so, you know, this is going to be exactly the same. So I'm not going to kind of plug all that in. And then we know the angle here for element B is 180 degrees. And so if you plug all of that in, what you get is a stress of minus 43,100 psi. Okay. And since this stress here is negative, this tells us that element B is in compression. Okay. Right. So once you solve for the nodal displacements, you know, computing the stresses is just kind of plugging it into this formula here. Right? So it's you know, it's a long process. So, you know, once again, you know, an example here took us half the lecture, but a lot of it is kind of, you know, mechanical. So kind of once I think the first few times you do these problems, it's really time consuming just because you're still kind of, learning, what's the formula for this element stiffness? How do I plug this in? But once you kind of get used to the process, then it's all kind of the same. Right? And then once we start doing beams and frames, it's all, all of this is going to be the exact same process. It's just, different formulas. Okay. Any questions on this? Okay. So there's one more thing I want to go over before we get into beams, which is how to leverage symmetry in a structure. Okay. So symmetry is actually a very important concept in finite elements in general, right? Especially in ANSYS too, because what symmetry allows you to do is that it allows you to kind of cut down the size of your problem at least by half, but sometimes even by fourths. Okay? And that's a big deal. Okay? And so I had several of you, kind of reach out to me from the previous activity about the mesh with the 2.5 millimeters, right? And so a lot of you ran into that error where ANSYS tells you that you've exceeded the problem limits for your license. Okay. And so what that basically means is that you have too many elements in your mesh. Right? And so with symmetry, basically what you can do is you can basically use the exact same mesh density, but just cut your geometry in half. Okay. And so let me show you what I kind of mean. So let me kind of draw a structure here. And so let's say that we have a structure that looks like this. And so we have 4 elements. Okay, so I'll label them A, B, C, D. Okay. And we have 5 nodes. Okay, so we have node 1, 2, 3, 4, 5. Okay. And so, and then let's apply a load. Okay, so our load here is going to be on node 3. All right. And so let's say that, you're asked to kind of solve this structure using the method that we just went through, right? And, you're looking at the structure and you're kind of, probably saying some not so nice things about me because you saw how long it took us to do a 2-element structure before. This is literally twice as much work because we have 4 elements and 5 nodes. And so to actually, go through the whole, compute the element stiffness matrix, assemble, solve, and stresses and all that stuff, it's going to take you some time, right?
You're the worst.
And so, what you can do from here is you can actually simplify this. You actually don't have to do the whole problem, right? Because what you should notice is that if you draw a line here, okay, if you draw this line here, what you should see is that this structure is the same on the left side as on the right side, right? And so, just like Jonathan's saying, we have a symmetrical a system. Okay, that's true. Yeah, most of these displacements will be 0 because we have a lot of pins. But it's still a lot of element stiffness matrices to do. And so if we have a symmetrical system like this, we can just say, why bother solving this whole system? Or we can just solve half of it. Okay. And so instead of solving that big thing, let's just solve, let's say let's just solve the left half. Right, and so the left half just looks like this, okay? And so this is nice because it's half the work, right? So it's half the elements and only three of the nodes, okay? All right. Oh, so a question in the chat. So the question is, if some were pinned on one side and the other side were not pinned, say they're rowers, would be able to use symmetry. And so in that case, you can't. And so not only does the geometry needs to be symmetrical, but the boundary conditions need to be symmetrical as well. And so if one of these supports here were changed to a roller, then this situation is no longer symmetric because you have a roller on one side and a pin on the other. Okay. And so everything basically needs to be symmetrical here. Okay. And so since we're cutting the structure in half, we need to cut the load in half as well too. Okay, so we're only going to supply P over 2 because we're basically saying the other half of the structure is basically supporting the other load. Okay. And so that's you know, that's a nice thing. So we can cut the structure in half. But there's one more thing that we have to do as well. Okay. And so whenever we make what's called like a symmetry cut, okay? And so basically, you know, we cut this structure in half. Right. Whenever we make a symmetry cut like that, what you have to do is you have to basically make sure that the structure doesn't displace past that symmetry cut. Okay? And so to do that, you basically have to apply a roller wherever you make a symmetry cut. Okay, and basically that makes sure that the structure doesn't, you know, displace past that. Okay, because if you had any, in this case, if you had any horizontal displacement at node 1, then you technically wouldn't have a symmetrical structure, right? And so that's we call this a symmetry boundary condition. This basically makes sure that your structure actually stays symmetric. Okay, and so, you know, in ANSYS you can actually do this too. So in ANSYS you can apply, you know, what's called a symmetry boundary condition. Okay? And so some of you might have noticed that when you were applying the pressure or the fixed support from the previous one. Okay? And so when you apply a symmetry boundary condition, what you're telling ANSYS basically is that there's, you know, I'm only simulating like half the structure here, and the other half of the structure looks exactly the same as what I'm showing you right here. And so what that tells ANSYS is that, you know, on this face that you're applying this symmetry boundary condition, you know, you can have a displacement that goes in the plane of that symmetry. Okay. But you can't have any displacement that goes past into that plane. Okay. And so that's basically what's happening under the hood when you apply a symmetry boundary condition in ANSYS. And with hand calculations with direct stiffness, this is how you would do it by hand, basically. Okay. All right. Any questions on this? All right, so the question is, can the symmetry cut only be applied vertically? No, so it can be applied in any direction. So basically, whenever you have, you know, symmetry in your problem, it can be, you know, you can have a structure that looks the same on top and the bottom. You can apply a symmetry cut horizontally like that, or, you know, if you have something that's slanted, you can, you know, you can do a symmetry cut slanted as well. So it's basically wherever you have symmetry, you know, that's where you're going to make the cut. Mm-hmm. Yeah, it's actually, you know, it's something that a lot of people kind of forget about once they kind of go out there and do finite elements in practice, that you can use symmetry like this. And actually, you know, a lot of structures that you end up analyzing, you know, in engineering are symmetrical. And so, you know, you can do this and you can cut your finite element costs in half, right? And, you know, everyone's always happy with that because you get your simulation results faster, you use less computing time, you use less memory, your manager's happy, you know, everything's good in your life. Okay, so that's everything that has to do with trusses. And so now you should be able to do everything in the homework. Okay, and so now, you know, for the last kind of 4 minutes of class, let me introduce kind of the next topic that we're going to go over, which are beams. Okay. All right. And so up to this point, you know, we've been doing springs and trusses. Okay, and just like we mentioned before, you know, all these elements are the same in that they can only be loaded in compression and tension. Okay. So you might have something that looks like this, and then the displacements that we compute are going to be in line, you know, with the element. Okay. Oh, this is D2. Sorry. This is D1, D2. Okay. These are hats. Okay. And so that's, you know, all that's fine, and that's kind of a good place to start. But we know that in reality, you know, structural elements, they have displacements that are a lot more, you know, complex than this. And so in the real structures, we have displacements that go, perpendicular to this, and you can also have rotations as well. And so in reality, we have situations that look just like this. And so, you might have a displacement that goes like this. Okay? And so we'll call this D1y and D2y hat. Okay. These are x displacements. Okay. And so now we have y displacements that are perpendicular to its local coordinate system. Okay. And we also have rotations. And so we can say that this node is rotated with an angle θ1, and this node here is rotated with an angle θ2. Okay. And so, with this combined with our, truss elements, then we're able to model basically any kind of complex deformation that a structure might have. Okay. And so just a little bit of terminology right here. So let's call D1y hat and D2y hat. Okay. And so we'll call these transverse displacements. And so they're transverse because they're acting kind of transverse to the axis of the element. Okay. We also have θ1 and θ2, and these are rotations. Okay. And so the rotations are there to basically allow you to model, if your element is kind of rotating, right? Because you might have a situation where your element, the node, it might not displace, but it can actually rotate. And so that causes a change in kind of orientation of the element, okay? And so what we'll see on Thursday is that, we can model these, transverse displacements and rotations. We just need a different element stiffness matrix to kind of, account for this, okay? All right, any final questions on anything we covered today? Okay. So that's all we got time for today. And so on Thursday, we'll pick this up with beam elements. And so we'll talk about the element stiffness matrix, and then we'll do some problems to kind of show you how to use it in practice. Okay. All right. So thank you everyone for tuning in today. Remember the homework. Homework 2 is posted. It's all about truss stuff. So you'll have everything you need to do in the homework. And so definitely get started on that because it can be a little bit time consuming. Okay. And so get started, and then let me know if you have any questions. So thank you guys for tuning in, and I'll see you guys on Thursday.
Professor, are we going to need ANSYS anytime soon or no?
Not for a couple weeks. And so
Okay.
my plan right now is we're going to finish up beams and then the last structural element, which is frames. And that'll basically cover all the theory that's going to be on midterm 1. And then we'll pick up ANSYS again after that.
Okay, yeah. Perfect. Thank you.
Mm-hmm.
Is this homework coming up, is it due next week?
It is due, let me check. It is due March 2nd, or February 23rd, sorry. So that is next Tuesday. So it's due a week from today.
Thank you.
Mm-hmm.
Professor?
Yep.
On problem, let's see, 3 of the homework, part B, I had a quick question about the angles.
Sure.
So on that truss problem, we have the setup where you have one at, I believe it's 0 degrees, one at the 45 from the down from the horizontal, and then 60 from the down.
Yep.
When we are doing our angles for cosine and sine, would we have to do that like 60 is like 300 degrees, or would that be like 120 degrees the other way?
Yeah, so for that one, so element A with the one that's kind of 60 degrees down, for that one you would use 300 because you would
300. Okay, so it is from the horizontal that we should. Okay, gotcha.
Right. Mm-hmm.
Okay, that was my question. I wasn't sure if we would if it mattered if we flipped it.
It does matter because it affects the signs of the sines and cosines. So yeah, if you use 120 for that, you're going to end up with some opposite signs in there. Yeah.
Wait, how come 120 wouldn't work for that though? Because it's on the same line, but I get why like the signs flip. I just don't get why it wouldn't work.
Right. So when you're plugging it into the global system, remember, because all these element stiffness matrices have to interact with each other in kind of the right way. And so if you had the sign wrong for like one of them, and then you add that together with terms from the second element stiffness matrix, you might get some terms to cancel out, or you might get some terms to add up. That's not actually true. And so, you know, all the signs kind of need to be correct so that all those interactions are correct.
Well, like what if I did that opposite for all of them? Like instead of 300 for 60, it was the 120, and then the 45 was 135, and then the bottom one I guess would be 90, or I guess 180.
Yeah. So if you use kind of the same kind of format for all of them, then that'll work. It's just you have to be consistent with everything.
Gotcha. So I could do either, just I have to be consistent.
Exactly. And when you apply your forces, so you know when you apply the your loadings of P, make sure that those are also consistent with your with your coordinate system too. Yeah.
Gotcha. Okay. Sounds good. Thank you.
Yeah. Do you guys have any other questions? Okay. So there's no more questions. I do have to run because I have another lecture right now, but email me if anything or send me a message on Discord. All right, so have a great day. I'll see you guys on Thursday.
See you.
See you.